So back to our table. We can draw a graph of the response of one of the factors. It doesn't matter which one. You can do this yourself using factor B. Here I'm going to use factor A. We have level 1, which was the lower level, and we have level 2, which was the higher level, and we have up here the response. So 100, put that in as 50. Okay, so for factor A, at the lower level for factor A, we had the average responses of 73 and 60. So let me try and put this in. Here we had 73, and here we had 60. This is the response of factor A when it's at the low level. Now when factor A was at the high level, we had the responses 48 and 83. And so here it is at the high level, we have 48 and 83. So this just shows us then the responses for factor A at the low and high level. Now, what we're interested though is to see what happened with factor B. So when factor B was both at level, the low level here, this is factor B low, we had the responses 73 and 48. So what I'm showing here then is factor B low. And when factor B was high, we had the responses 60 and 83. So this is factor B high. And what you notice from the graph here is that the response changes. The response in factor A goes from low to high when factor B, from low to high when factor B is high, but from high to low when factor B is low. And this means that there's an interaction between the factors A and B. If there were no interaction, these lines will be parallel and they would not cross each other. So we could already see here graphically that there's an interaction, a strong interaction between the factors A and B. And maybe it's also easier to understand what interaction means. When a response changes in one way between two levels of one factor, but then changes the opposite way when the factor is changed, then we have the interaction. So, unfortunately for this case, when interaction exists, the calculation of our main effects become meaningless. All the work we did to get the -1 and the 11, we can't use those values because the interaction means that the response behaves differently at different levels of the other factor. So we simply have to go back to where we had before. We look at the different treatment combinations at which the trials were run, and we choose, as we knew at the beginning, the treatment combination that produces the best response. And here we had the best response, the lowest mowing time when factor A was at level 2 and factor B was at level 1. And this method of selecting the best combination of levels is just called running with the winner. Because we have interaction, we are not able to use our effects, but we can look at our experiment and see what was the best result. And this means that we don't use any more of our data anymore to investigate the responses, but we could design maybe a different experiment. Now, that completes the 2x2. We just want to have a few words about the 2x3 design, because this is used when instead of having just 2 factors, we have 3 different factors. So in this case, we have A, B, and C, representing the high levels of our three different factors. And of course, with that, we would have then 8 possible treatment combinations if there's 2 replicates, which is a total of 16 runs. And these runs have to all be, of course, randomized, which takes money and time. We can also, though, create a table, which, with our treatment combination codes, we have the 3 factors, we have the interactions, and including this time an interaction between all 3. We have different replicates, we have responses, and we can calculate the contrast and effect. So there's some details in our textbook on this. But the major problem with this type of design when you get to higher levels above 3 is the number of trials increases exponentially, and even if we use just one single replicate. And if you do multiple replicates, then the number of trials becomes impractical. So for example, if we have k equals 5, so we have 5 different factors and we need 2 replicates, we need 64 trials, which is very, very high. And so therefore, statisticians have derived different methods to eliminate the need for a second replicate. And they have also devised what's called fractional factorial designs, which call for running only a fraction of the total number of runs in the full factorial. And the fractions are being chosen in such a way that you get the most useful information from the experiment. And again, we're not going to cover that in this course, but there are details in statistical textbooks and also in our textbooks if you're interested.